Let's continue on by talking about linear and angular speed. We recall that the length of a circular arc is given by the formula S equals theta times r. So S stands for circular arc, theta is the angle, and r is the radius. And you can use this information to analyze the motion of a particle moving at a constant speed along a circular path. So consider a particle moving at a constant speed along a circular path of radius r. If S is the length of the arc traveled in time t, then the linear speed of the particle is given by the formula v equals S divided by t. So linear speed measures how fast the particle moves along that circle. You could also write this formula as v equals theta times r over time. So this is the angle and the length of the arc divided by the time that it takes the particle to move. Also, if theta, the angle corresponding to the arc length, then the angular speed of the particle is given by the formula, it's not a W, it's actually a lowercase omega. So this is the Greek letter omega, which I just spelled wrong. So the angular speed is omega, which is going to be equal to the central angle divided by time. Okay, so let's do an example of one of these. The second hand of a clock is 10.2 centimeters long. Find the linear speed of the tip of the second hand as it passes around the clock face. So here's our clock. Our radius is 10.2, and we're interested in the tip of the second hand as it goes around the clock, like that. So I've given you a hint. It says find the arc length and the time for one full revolution. Arc length is going to be S, but remember that S is the radius times the angle. Well, one revolution is going to be all the way around the circle. That's the circumference, which is 2 pi r. So if we have one full revolution, we're going to end up with our formula looking like this. Let's use radius times theta over t. So our radius is 10.2. Our full revolution is 2 pi, because in radians, that's what it is all the way around a circle. And the time it takes the second hand to go around the clock face is 1 minute. So that's 60 seconds. Now that we've set that up, we can take that information, plug it into our calculator. Make sure that you use the control equals, because you want an actual value for your speed here. So you get 1.068 centimeters per second. This includes, make sure you include a unit. And since we're talking about speed, units for speed are always going to be distance divided by time. So you got to have a time unit, that's the centimeter part. And then you got to have, the distance part is the centimeters, and the time part is the seconds. All right, let's look at example 2. The hour hand on your watch is 1 centimeter long. Find the linear speed of the tip of the hour hand as it passes along the clock face. So again, let's talk about the information we have. We know our radius is 1 centimeter. We know S in this case is going to be the radius, which is 1, times the distance around the face, which is 2 pi, because that's one revolution around the face. And how long does it take the hour hand to go around the clock face? In this case, our time is going to be in hours, and the arm of the hour hand takes 12 hours to make one rotation. So our time ends up being 12 hours. So when we set up our equation, we're going to have the speed is going to be equal to the arc length times theta over the time. Our arc length is 2 pi. I'm sorry, theta is 2 pi, and our arc length, our radius is 1, so that would, our arc length does end up being 2 pi. And that's going to be divided by 12 hours. In the end, when we put that into our calculators, we get 0.524 centimeters per hour. All right, let's do this third example. A Ferris wheel with a 50-foot radius makes 3 revolutions every 2 minutes. Find the angular speed of the Ferris wheel in radians per minute, and then find the speed of the linear speed of the Ferris wheel. So angular speed is this formula. Omega is equal to the central angle over t. And what that means is we're measuring how fast that central angle is getting bigger as it goes, or getting bigger, or getting smaller as it goes around the circle. So in this case, we'll just write down the radius is 50 feet. We don't necessarily need that. Theta, in this case, it's 3 revolutions every 2 minutes. So 1 revolution is going to be 2 pi. And if we do 3 revolutions, that would be 6 pi. So our theta is going to be 6 pi. And then the time it takes to do that is 2 minutes. So for our formula, we're going to have omega equals 6 pi divided by 2 minutes. So that's going to be equal to 3 pi radians per minute. So that's the change in the measure of the angle over time. Then to find the linear speed of the Ferris wheel, now we're going to use our linear speed formula, r equals s over t, where s is the arc length, or we could do r times theta, v equals s over t, or we could do v equals r times theta over t, which in this case, r is 50. Theta, we've discovered, is 3 pi, and the time it takes to go 3 pi is 1 minute. We figured that out last equation. So here, when we multiply all these things together and get a equivalent, decimal equivalent, we get 471 feet, 0.24, and this is going to be feet per minute. And again, make sure you have a unit because you're talking about a speed, so I had a distance per minute. For the angular speed, I had radians or degrees per minute.